going to talk about the physicist ideal chain model and the radius of gyration, how to make those calculations. So the physicist ideal chain model is the last one we're going to deal with. It's basically this idea that you can coarse grain your approach. And basically what we're going to do is we're going to approximate a little bit larger chains as freely jointed chain models. And we'll see this in a second. We basically do this change in variable of the number monomers n and l to n and b respectively to kind of look at this larger length scale, and we kind of coarse grain it, and we kind of coarse grain it based on, you can kind of see these change in variables here. So the physicist ideal chain model kind of takes into account a little bit of your kind of chemical information, but this model again is specifically made for the theta condition and the melt state. It does not account for any solvent at all. So all it does is kind of it's a little bit more refined model. Like the ideal chain model, there's no C infinity value here as well. So all of this physicist ideal chain model is encapsulating those bond angles theta and phi and a little bit of like excluded volume terms, obviously, but not incorporated into the solvent. So we can kind of take a look at that in our presentation on how it's done. It's just a coarse grain model. It's not, hopefully it's not too cumbersome or too exciting necessarily, or not too exciting. I mean, it should be, I don't want to downplay the physicist ideal chain model. It's very, very exciting, but we will kind of talk about that a little bit later. So let's see. So yeah, so this is effectively what we're doing. We're going from our ideal chain model here to this new coarse grain model. So you can see that the B length is greater than L. So we're just kind of coarse graining it. We're kind of, coarse grain model basically assumes like you're treating this kind of almost as like this like ball and stick model here. So we're coarse graining it, we're making it larger, and it's taking into account, again, the key thing, taking into account those bond angles. That's why kind of our monomer unit increases. And as you can see, the length of our chain is a little bit different as well. But yeah, so that's the physicist ideal chain model in a nutshell. Now, we've been talking about calculating RMSD, but we've so far been focused on kind of linear polymers. But we know that there's dendrimers, there's mecoarms, there's Staller polymers, there's brush, there's combs, there's block copolymers, there's all kinds of helical polymers, there's globulal proteins, there's all types of different kind of structures that we deal with polymer chains. So the question you might ask me, well, how do I figure out the length or the RMSD of this polymer or this polymer? Well, what you can do is do a calculation that's actually much more common when you look in the literature for polymers, which is the radius of gyration. So the radius of gyration is a very, very similar calculation. The key thing here is that we must first calculate the center of the mass. So center of mass for our polymer, as we kind of go out in some distance r, so we need to know kind of, again, the molecular mass of each of these kind of components or arms of our polymer. So the calculation gets a little bit messy. But you can kind of basically, assuming that your mass is the same for all monomers, which is very good assumption, except for, again, those block copolymers. Unless you coarse grain a block of polymer, if it's a repeat, if it's basically a periodic polymer, a random block of polymer, that's going to be really kind of tricky. But radius of gyration is just going to be mean squared end-to-end distance from the center of mass divided by the number of monomers. So you can kind of go around and you can kind of play around with that model. We're not going to talk about it too much in this course, but we wanted to make sure that you knew, basically going forward, that radius of gyration, very, very, very similar. But again, it just takes into account first the center of mass, and then it calculates your RMS distance. And actually, what's pretty cool is that we can kind of discuss this derivation later. I know you all love derivations, but we could relate the radius of gyration to the ideal linear chain model, so that freely jointed chain model, using this relationship right here. So very, very simple, straightforward. But again, this only holds for freely jointed chain. So this does not hold for our chemist model, for the physicist model, for anything else. So make sure you keep that in mind. But again, if you're looking at an ideal state, if we're looking at theta solvent, we're looking at the melt, we can use this. So yeah, that's what basically, really, really briefly, the physicist ideal chain model. Again, it's more I want you to know that moving forward. And again, you can see a nice kind of calculation schematic of that right here. Again, center of mass, radius of gyration, you calculate it out. But yep, that is the radius of gyration and physicist ideal chain model in a nutshell. So again, physicist ideal chain model only works for in the melt or in a theta solvent, and it calculates and it uses the basically takes into account bond angles as well. Yeah. Next time we are going to get into a really, really fun derivation of polymer swelling. So we know kind of qualitatively how polymers should behave in a good solvent or a bad solvent, but now we're going to get a little bit into the math, and we're finally going to meet our really, really good friend. We're going to get used to him a lot, Paul Flory. We saw in the first day of our class. So polymer physicist, Nobel Prize winner, and he is our leader in terms of our battle between entropy and enthalpy, which never stops with polymers, and especially conformational entropy and entropic spring effects. So we'll get into that next time. So I will, because we've done a very, very just kind of qualitative description of alpha, but we want to kind of look at real chains, how they interact, all those good stuff. So we will talk about that next time, and yeah, I'll see you in the next video. Thanks. Bye.